right, so get ready because today we are going deep into the mind of Albert Einstein. We're going to be unpacking excerpts from his own book, Relativity, the Special, and the General Theory. And let me tell you, when Einstein starts talking about space and time and gravity, things get really, really mind-bending.
You know, what's so fascinating about Einstein is how he just tackles these huge concepts that even he admits are, like, tough to really wrap your head around. Like the idea of space, it's something we experience all the time, constantly, but actually trying to define it, that's where things get a little slippery.
It's true. So how does Einstein even begin to approach something as, like, fundamental as space?
He really encourages us to move away from this idea of absolute space
Yeah.
and instead focus on relative motion. And one of the best examples he uses is imagine dropping a stone from a moving train.
Okay, I can picture that. So what happens to the stone?
But to someone on that train, the stone looks like it's just falling straight down. But to a person who's standing on the ground watching that train go by, the stone's path actually looks like a curve, a parabola.
So the stone's trajectory isn't like this fixed, independent thing. It literally changes depending on where you're looking at it from. That's crazy.
Exactly. It shows how motion is always relative to like whatever reference point you choose. And this brings us to what Einstein calls Galilean systems of coordinates.
Okay, that sounds pretty complicated. Can you break that down for me?
Think of it as a system where the law of inertia, that holds true, but instead of just like stating the law, let's think about how Einstein approaches this. So picture looking at a star, a really distant star. From our perspective here on Earth, it looks like it's pretty much staying still, right? Like it's following that law of inertia, staying in motion at a constant speed.
Right. We learn in school that the stars are moving, but they're so far away that it looks like they're standing still.
Yeah, exactly. So for a long time, people used the stars as this fixed reference point, and it worked pretty well. But what happens if we shift our perspective a little bit and use the Earth as our reference point? Suddenly, those fixed stars look like they're actually moving in circles around us.
So Newton's first law, the foundation of classical mechanics, kind of starts to fall apart when we change our perspective.
Yeah, it highlights how even something as seemingly fundamental as inertia might not be as absolute as we once thought.
So we've got motion is relative, there's no such thing as absolute space, even the concept of inertia is up for debate. Where does Einstein go from there?
Well, that's where he brings in another huge idea, the speed of light. And it seems pretty straightforward at first. Light travels in a vacuum in a straight line at a constant speed, about 300,000 kilometers per second.
Right, that makes sense.
But here's the thing. That speed is the same no matter what color the light is. And scientists figure this out by looking at eclipsing stars and this whole idea that the speed of light is constant that led to this really interesting conflict with this thing called the principle of relativity. And that principle says that the laws of physics should be the same for all observers who are moving at a constant speed.
Okay, I think I'm starting to see the issue. If motion is relative, shouldn't the speed of light look different depending on, like, how fast you're moving?
Exactly. And it's this observation, this seemingly simple observation about the speed of light that really sent Einstein down this path to completely change how we understand space and time. And then, to make things even more wild, he introduces this idea that simultaneity is relative.
Wait, hold on. Simultaneity being relative, what does that even mean?
Okay, imagine this. 2 lightning strikes hit the ground, and they hit at the exact same time according to someone who's standing still on the ground, right? Now picture another person. This time they're on a train that's zooming past at a constant speed. Because that train is moving towards one lightning strike and away from the other, those 2 strikes actually won't look simultaneous to the person on the train.
So the lightning strikes are simultaneous for one person but not for the other. How is that even possible?
It's possible because time itself is relative. Time isn't this absolute universal thing that's ticking away for everyone the same way. It's actually all tangled up with space, forming this kind of flexible fabric that we call space-time.
Wow, okay, my brain is already doing backflips trying to understand this. It's like everything we think we know about the world just completely shatters.
And that's where Einstein's genius really shines, He wasn't afraid to challenge those really deep-seated assumptions and to follow the logic of his ideas, even if it led to these conclusions that seemed like completely paradoxical.
Okay, so if simultaneity is relative and time itself is relative, then how do we even begin to make sense of the universe?
Well, this is where Einstein starts talking about this idea of a continuum. and this really amazing world of non-Euclidean geometry. It might seem like a jump, but trust me, it all connects.
All right, you've got my attention. Let's dive into this geometry thing.
So Einstein uses the example of a smooth marble table to get at this idea of a continuum. Imagine moving across the table, smoothly without any jumps, right?
Yeah, I can picture that. It's a continuous surface.
Now imagine that you're building a grid on this table, but you're using these small identical rods. In Euclidean geometry, the kind we all learned in school, we'd expect those rods to form perfect squares, right? With diagonals that are all the same length.
Right, that's like basic geometry stuff.
But here's where things get interesting. What if that table itself isn't perfectly flat? Or what if things like temperature are affecting those rods as you're building this grid?
So you're saying that on a curved surface, or if our measuring tools are being messed with, those perfect squares might actually get distorted.
Exactly. And that's where these things called Gaussian coordinates come in. They're this more flexible system for mapping out locations, even when we're dealing with curves and these variations.
So it's like a more adaptable way of mapping out locations, even when things aren't perfectly straight or even.
Precisely. In this world of non-Euclidean geometry, the relationship between distance and coordinates gets way more complex. And that has some really big implications when it comes to understanding spacetime.
Okay, I'm starting to see how this all links together. But how does non-Euclidean geometry actually apply to the real universe? Is our universe non-Euclidean?
No, that's a great question, and it leads us right into Einstein's concept of spacetime and how it's affected by gravity.
All right, I am hooked. Let's unpack that. So we've established that our universe might not follow these nice straight lines of Euclidean geometry. What's the connection between this non-Euclidean world and the whole idea of space-time?
Well, Einstein actually found that in special relativity, the distance between events in spacetime, it stays constant no matter what your reference frame is. And this leads to this thing called the Lorentz transformation, which is like the mathematical backbone of special relativity.
Okay, the Lorentz transformation. That sounds pretty complex.
It is. But think of it this way, imagine two people are observing this moving object, right? One person's standing still, and the other one's on, say, like a train moving alongside the object. The Lorentz transformation basically helps us connect the measurements that those two observers would make about the object's length, the time it takes to travel a certain distance, even its mass.
So even though space and time are relative, there's this underlying constant that's like woven into the fabric of space-time.
Exactly. And this is where things get really crazy. Remember those Gaussian coordinates we talked about?
Uh-huh.
The ones we used to map out those curved surfaces? Well, it turns out they can also describe the curvature of spacetime itself.
Wait a minute, you're saying space-time isn't this flat, static thing. It can actually curve.
Yeah, that's exactly what Einstein proposed. And what's even more mind-blowing is that the way matter is distributed, it actually affects this curvature. And that's where gravity comes in.
Hold on, are we saying that gravity is actually connected to the curvature of space-time?
You got it. Instead of thinking about gravity as this force that's pulling objects towards each other, Einstein kind of reimagined it as a consequence of this warped spacetime.
Okay, that is a huge shift in thinking. I think I'm going to need a little more help to really wrap my head around this one.
Sure, no problem. Let's think back to that example of dropping a stone from a train, right? Remember how the stone's path looked like a straight line to the person on the train, but it looked like a curve to the person standing on the ground?
Yeah, it showed how there's not just one true path. It all depends on, your frame of reference.
Right. Now, Einstein basically argued that the same principle applies to gravity. So instead of thinking about the Earth pulling that stone down with some kind of force, picture the Earth as warping the space-time around it, like it's creating this kind of dip. The stone then just follows the curvature of that dip, and we perceive that as the stone flailing because of gravity.
So it's not that the Earth is pulling the stone, but rather the stone is following the shape of space-time that's been, distorted by the Earth's mass.
Precisely. It's kind of like, imagine rolling a marble on a trampoline. If you put a bowling ball in the middle of that trampoline, it's going to create a dip. Right? And the marble's naturally going to roll toward that bowling ball. It's just following the curve.
That's a great analogy. So the Earth is like the bowling ball warping the fabric of space-time, and the stone is like the marble, just following the curve. But if gravity is all about this curvature, how did Einstein explain why all objects fall at the same rate, no matter how heavy they are? Shouldn't a bowling ball create a bigger dip than a marble and therefore fall faster?
Ah, that's a really good question. And the answer actually lies in the fact that heavier objects, while they do create a slightly deeper well in space-time, they also have more inertia. That resistance to change in motion we were talking about earlier.
Oh, right. So it's like there's this kind of cosmic balancing act going on. The increased curvature from a heavier object is balanced out by its greater inertia.
Exactly. It all works out in this really elegant way so that in a vacuum, all objects fall at the same rate, regardless of their mass. It's one of those like beautiful symmetries in the universe that really makes you appreciate the power of Einstein's thinking.
Okay, so gravity is the curvature of space-time. But didn't Einstein also predict that this curvature could actually travel like waves?
Ah, you're talking about gravitational waves.
Yeah.
That was another one of those like mind-blowing predictions that came out of his general theory of relativity. He realized that if space-time could be warped by these massive objects, then those warps could actually ripple outwards, like waves spreading across, a pond.
Gravitational waves, actual ripples in the fabric of space-time. It's almost too incredible to even imagine.
I know, it's pretty amazing. And for decades, this whole idea of gravitational waves was just a purely theoretical concept. But then in 2015, scientists actually did it. They were able to directly detect gravitational waves for the very first time. And get this, they were generated by two black holes colliding billions of light years away.
Wow. Detecting ripples in space-time from an event that happened billions of years ago. That's just, wow.
I know, it's incredible. It was a huge moment in science. It confirmed yet another one of Einstein's predictions, and it just further solidified his general theory of relativity as one of the best, most accurate descriptions we have of how gravity works on this, like, huge cosmic scale.
So going back to this idea of no independently existing trajectory, what did Einstein actually mean by that?
Yeah, it all comes back to how we actually describe the position of things, of objects. Think about how we usually talk about where something is in everyday life.
Hmm.
We might say it's next to, a landmark or it's a certain distance from some fixed point.
Maybe like using a map or giving directions.
Exactly. But Einstein pointed out that these descriptions are inherently dependent on, whatever reference point we choose. There's no universal coordinate system that exists independently of our observations.
So even something as basic as saying where an object is, that's relative too.
Precisely. And this realization, it really forced physicists to rethink how they described motion and position, especially when they were dealing with those extreme scales and speeds where relativity really comes into play.
So instead of relying on those fixed points, how did physicists actually adapt to this new understanding of relative position?
Well, they turned to this system that had been developed a while back, actually. It's called the Cartesian coordinate system. You remember those X, Y, and Z axes?
Oh, yeah, vaguely. I kind of remember like plotting points on those in math class. But what's so special about the Cartesian system?
Well, the really cool thing about the Cartesian system is that it lets us describe locations without needing to rely on those physical markers. We use 3 perpendicular planes, and each one has a numerical scale, and that lets us pinpoint the exact location of any point in space.
So it's like we're creating this invisible grid that we can use to map out the entire universe.
Yeah, that's a great way to put it. And this system became really crucial for understanding all the complexities of relativity, whereas, the very fabric of space and time is all flexible and dependent on those reference frames.
Okay, this is just fascinating. I'm really starting to see how even like those really basic concepts, like just describing where something is, had to be completely re-examined in light of Einstein's ideas. But I've got to admit, my brain is starting to feel a little fried. We've covered so much ground, from relative motion to the curvature of space-time to gravitational waves.
Yeah, it's true. We have. And we've only just scratched the surface of Einstein's mind-blowing theories.
I can't wait to dive even deeper, but I think for now, let's take a moment to process everything we've learned so far. All right, I think my brain is feeling a little less fried now. So before we wrap things up, I want to make sure I'm really getting this whole, gravity thing. It's a pretty big change from what Newton was saying, right?
Oh, absolutely. Newton saw gravity as this mysterious force that could act across huge distances and instantly affect things with mass.
Yeah, like the Earth pulling on the moon or, an apple falling from a tree. It's like a pretty intuitive way to think about it.
Yeah, it's definitely intuitive, but then Einstein comes along and totally flips the script, right? He's basically like, forget about gravity being a force. It's all about the curvature of space-time.
So instead of a force pulling things together, it's the actual shape of space-time itself that determines how things move.
Exactly. It's kind of like, imagine you've got this bowling ball and you put it on a stretched out rubber sheet. The bowling ball is going to create a dip in that sheet. Right?
Yeah, like a little dent.
Right, so think of that rubber sheet as space-time, and the bowling ball as, say, like the sun. The sun's mass actually warps the fabric of space-time around it, creating this gravitational well.
Oh, okay. So the planets that are orbiting the sun, they're not really being pulled toward it by a force, but they're actually following the curvature of space-time that's created by the sun's mass.
That's a great way to visualize it.
Right.
It's not like those planets are being tugged toward the sun. They're just traveling along the curved path that's been shaped by that sun's distortion of spacetime.
That is incredible. But if gravity's all about curvature, like how come a heavier object doesn't make a deeper well, you know? And shouldn't that make it fall faster? Like a bowling ball should make a bigger dip than a marble, right?
That's a sharp observation.
Hmm.
And the answer is actually that heavier objects, they also have more inertia. That resistance to change in motion we were talking about.
Oh, right. So it's like a balancing act. The increased curvature from that heavier object is balanced out by its greater inertia, right?
Exactly. It all works out so that in a vacuum, everything falls at the same rate, regardless of how much mass it has. One of those, like, elegant symmetries in the universe that really makes you appreciate how brilliant Einstein was.
Okay, so to sum it all up, we've learned that motion and time are relative, simultaneity is relative, and gravity isn't a force, it's a curvature of space-time. And even just how we talk about location, where something is, that has to be adaptable too. My head is spinning, but in a good way.
I know, it's a lot to take in. But what's even more amazing is that all of these ideas, these concepts, they actually have real-world consequences. Like we can observe them in the universe.
Right, like that whole thing about gravitational waves, these actual ripples in the fabric of
Yeah.
space-time, it's just mind-blowing.
I know. For decades, it was just like an idea, a theory. But then in 2015, scientists actually detected gravitational waves for the first time. They were caused by two black holes colliding billions of light years away. Can you believe it?
Wow. Detecting ripples in space-time from an event that happened billions of years ago, that's just wow.
It was a huge deal for science. It confirmed one of Einstein's predictions, and it just like cemented his theory as one of the best descriptions we have of how gravity works on a cosmic scale.
So what does all this mean for us, How does understanding relativity change the way we see the universe and, like, our place in it?
Well, I think it challenges us to rethink some of our most basic assumptions about reality.
Yeah.
Like the universe isn't just this static background where things happen. It's dynamic, it's evolving, space and time are intertwined, and gravity is a consequence of the fabric of existence itself.
It's so mind-boggling. But it's also really inspiring. Einstein opened our eyes to this universe that's way more complex and amazing than we ever could have imagined.
Absolutely. And his theories, they opened up all these new areas of research, like studying black holes, the evolution of the universe, even this search for a unified theory that would like connect gravity with the other fundamental forces of nature.
So even though Einstein totally revolutionized our understanding of the universe, there's still so much more to explore. So many questions we still haven't answered.
That's the beauty of science, right? It's a journey, a constant search for answers. Who knows what incredible discoveries are waiting for us as we, keep digging into Einstein's work and pushing the limits of what we know.
Well, I think it's safe to say that our deep dive into Einstein's world has given us a lot to think about. It reminds us that even when we're dealing with concepts that seem, almost impossible to understand, our minds can actually grasp and appreciate the beauty and complexity of the universe.
And for anyone listening, don't be intimidated by these ideas. Just keep asking questions and keep exploring. You never know what you might discover.
So, to everyone out there listening, keep questioning, keep wondering, and keep exploring this amazing universe we live in. We'll see you on our next deep dive.
Loved this video? Smash that like button and subscribe so you don't miss out on future content. And don't forget to order the book, link below.